Hello, everyone. Welcome to our tutorial, AI meets database. So good morning, good afternoon, and good evening, everyone. So in this tutorial, we will first introduce AI4DB, which wants to utilize AI techniques to optimize database. For example, we use deep learning to estimate the cardinality and cost of a query, so which can improve the accuracy for estimating the cardinality for multiple fields or multiple tables. And we can also use some reinforcement learning techniques to tune the knobs, which can also increase the performance of the database. We can also use some learning-based technique to recommend some index views to enhance the database performance. On the other hand, we also want to introduce database for AI. So we want to utilize database automation techniques to reduce the burden of deploying AI. So you know that when the user want to utilize AI, they want to load data outside the database and then train the data and utilize data. It's rather inconvenient for users to deploy AI models. So our database community want to embed AI capabilities inside database. So we can extend CQ to support AI operations, and we want to develop database operators and automators and increase the training time and improve the training performance and the inference performance. So this is the outline of our tutorial. I first introduce AI for database, and then we will introduce database for AI, and finally we will provide some challenges and open problems for AI for database and database for AI. So I first introduce some motivations of AI for database. So we know there are many new scenarios that bring new challenges for traditional database techniques. For example, we have various applications, and we have large-scale data, and we have diversified workloads. So traditional database rely on human to tune the database, to optimize the database, which are not true for large-scale data, for example, on cloud database, because it's very human-intensive work to tune billions or millions of database instances on the cloud. So we must use some automatic techniques to help us to optimize the database and to make the database more intelligent and more powerful. And AI is also getting more practical due to three main driving factors, including we can handle large-scale training data, and we can have some more AI algorithm, and we have powerful new hardware, for example, GPU and AI chips. More importantly, different from some traditional machine learning and data mining, which aim to improve the accuracy. So they rely on some training data, and this training data should be labeled by humans. But in database, we focus on the improved accuracy and efficiency. So for efficiency, we can easily to get results by running some workloads. So we have large opportunity to utilize machine learning techniques to optimize database performance. So first application is about learned database configuration. You know that every database has large number of knobs. For example, PostgreSQL and MySQL, and some database has hundreds of knobs. And it's very important to tune knobs to achieve high performance. However, it's very labor-intensive tuning for traditional methods, which rely on some database administrator to tune the database. So it's very promising to apply automatic tuning methods. The second is that the traditional tuning is very time-consuming. It usually takes weeks of days to tune the database. So we can utilize some learning-based techniques to reduce the tuning latency. And another point I want to mention that the database administrator DBA usually can transfer the knowledge because they can utilize some knowledge and transfer knowledge to other database instances. But for the learning-based techniques, this is much harder than human. So when we apply machine learning techniques, we need to consider how to improve the adaptivity for the different database. For example, we want to the learning method to adapt to different workloads, different database instances, and different database systems and different hardware. So I think this is rather challenging, and the database community are working on this to improve the adaptivity for the uh, machine learning techniques inside database. So the second one is learner-based query optimization. So we can utilize machine learning techniques to address the harder optimization problem. For example, cardinality estimation. Traditional method usually utilize some histogram, sketch-based method. But for multiple columns and multi-tables, it's rather hard because different columns and different tables have some correlations, and the training methods are hard to capture the correlation. And the second one is join order selection. So for example, given 10 tables and there are billions of possible orders to join the tables. So it's very important to get a better join order. So if we want to explore every possible join order and then select the best one, it will take lots of time. So you know that selecting best order has two parts. The first one is select the order. The second one is utilize order to run the query. Both time are very important. We need to very quickly to identify the order, and the order can be run by the database very fast. So we need to find the best order very efficiently. So the third one is about learner database design. So you know that there are lots of work on learner index. The traditional B tree may have some problem, for example, concurrency and some size and some pointer chasing and catch miss in memory. So can we utilize some learning-based index to replace the traditional B tree index? There are many attempts to address this issue, and there are lots of work. And there are also some other learned data structure. For example, learned transaction scheduling. Can we schedule the transaction to avoid conflict between different transactions so as to improve the performance of running these queries? So I think there are lots of opportunities. And also some learned database diagnosis. I think this is also very important, especially on the cloud. You know that we have billions of database instances, and it's rather important to diagnose the system and slow queries. So can we utilize machine learning techniques to monitor database activities and diagnose the system and find the root cause for each failure? I think this is rather important. We can utilize some learning-based technique to help us to diagnose the database. And next is database security. So database security is also important. For example, how to automatically to discover the sensitive data and detect anomalies of database. For example, whether some user wants to attack database and whether we can detect the sensitive data, for example, the card number and the ID number. So we want to automatically to do this, not labeled by human. And we also want to avoid the SQL injection and some anomaly access of the database. I think this can also be relied on the learning-based techniques. And there are some database systems that also want to try to utilize machine learning techniques to enhance database. For example, Oracle wants to tune the knobs to to recommend the views, knob tuning, and open source new database that also utilize AI techniques to optimize the whole life cycle of the database system, and also including some database tuning index and view advisor, and they're also working on some kinetic cost estimation and joint order selection and auto tune. This is a new company by Anipolo that want to use machine learning techniques to optimize database to tune knobs. So I think there are lots of opportunities that deploys machine learning technique inside the database, and this call for arms from the database community to work on this and to make database community much stronger. Okay, next I will introduce some techniques for database for AI and AI for database. I will first introduce AI for database. I will first introduce some techniques, and then my students and college will introduce some other components. First, I want to introduce knob tuning. So the motivation is that there are lots of database knobs, and it's very important to tune the knobs to achieve high performance. More importantly, the knobs are correlated, and they have some correlations, and it's rather hard to tune the knobs. And the knob tuning also affects the database performance. The training database usually rely on DBA to tune the database, but for large-scale database instances, the DBA cannot tune many database instances. So we can rely on some machine learning techniques to achieve this. And the next, I will introduce a workflow of knob tuning. First, for example, a user finds that the database is slow, so can we tune the knobs and to make the database faster? The first step is that first the tuner, the automatic knob tuning system will request workloads in recent, for example, hours or weeks, and run the workloads on the database system, and then activate the workloads in the database system. After activate the workloads, we can get some matrix from the database. Based on the matrix, for example, we can find how can we tune the knobs. So there's some correlation. We can learn the correlation between matrix and knobs. And based on correlation, we can recommend how to tune the knobs. And we set knobs and to rerun some workload and recheck the metrics, and then we can tune the knobs further. So in this way, we can make the database run faster. So there are some challenges. For example, how to tune hundreds of knobs. And more importantly, the knobs are not independent, and most of the knob values are in continuous space. So it's rather huge space for the knob combination. So, so for database, can we effectively use large-scale data to tune the knobs? So you know that for the database vendors, it's rather hard to get some large-scale experience data, especially on the production machine. So because they do not want to remember many workloads. So how to get workloads to tuning knobs is also a challenge. So can we do not rely on large-scale training data, especially some data from the production machine or node. So the second, how to adapt the tuning method to different scenarios. For example, different workload, different system, database instance, and different hardware. I think this is rather challenging. So we can broadly categorize the existing tuning methods into 5 classes. The first one is a heuristic methods. In this method, they want to get some training data, for example, the training workloads, some workloads with some best knob tuning knobs, and then give a new workloads, they find some similar workload and recommend some knobs. This rely on the training data. The second one is machine learning pipeline-based method. So they was first one to categorize the workloads and identify the most important knobs, and then use the machine learning technique to tune the knobs. And the third one is untrained reinforcement learning-based method. So this method based on, for example, give a database, they want run some workload on database and then tune the database based on the workload running and some metrics report from database. And the deep learning, they also rely on some training data that capture the relation between the metrics and knobs. And the last one is there are also some works on tuning some memory-based database, for example, database and Spark, tune the buffer size. So the first method is search-based tuning method. So this is some heuristic-based method. First, they want to get some training samples. They divide some knob range into key intervals and sample some settings for each interval, and then give a new workload. They find some similar workload from this training data, and then based on the knobs for this training data to recommend the knobs. So this is rely on some training data. This is some limitations. So it wastes some time to searching the knobs, and it cannot learn from heuristic tuning, and needs to restart the procedure from scratch each time. And they also need some training data. The second method is about machine learning pipeline. So they first categorize the workloads and identify the most important knobs that may affect the performance, and then tune the knobs based on some machine learning techniques, for example, Gaussian process regression, so tune the knobs. So this is a pipeline-based methods, and it also needs to use some training data. So this pipeline architecture, so where the ultimate solution may not gotten because it may fall in some local optimum, and it's also rely on some high quality training samples. And if we have such training samples, it's okay. But if we have no such training samples, it's rather important to get there. The next method is end-to-end reinforcement learning for tuning. So this basic idea is that so we want to utilize some reinforcement learning to tune the knobs. So given a database system, and for example, this is a database system, and we have a tuning agent. So this is our tuning algorithm. So there are some actions. The tuning agent will apply some actions. The action means that we want to increase the value of knob or decrease the value of some knobs. So when we apply the action, so we run the workloads on the database, and the database will report some metrics. For example, the transaction commit number, the tuple fetch number, and some conflict number. And based on the metrics, we can capture the correlation between knobs and metrics. And we can also get the performance change after we do the action. So in this way, we can capture the correlation between the knobs and the performance, and the knobs between the metrics. In this way, we utilize correlation to do some new knobs. For example, give a new workload. We run the workload and we get a matrix. And based on matrix, we know, okay, how can we tune the knobs? So this is a pipeline. So for example, which knob we want to tune? For example, the cache size, the checkpoint timeout, IO concurrency. So we have six important components in here. Agent means the tuning system, environment, the database instance, and state, some metrics, and action, the tune the knobs. Policy is the how to capture the agent, and the reward means that after we tune the knobs, how can we evaluate the tuning? So this is the reward. So if the performance is better, we give a positive, otherwise we give a negative. So here are some important techniques we need to consider. For example, how to select good reinforcement learning methods. So because both the state and action. The state means the matrix, and the action means the knob tuning. So both of them are in continuous space. So we need to select algorithm that supports the continuous space. So it's important to select some policy-based method, for example, DDPG. The second issue is about the reward. So when we tune the knobs, how to evaluate whether the tuning is good or not. So the reward is important. So we need to capture both the long-term reward and short-term reward. So it's very important to design a very good reward function. So later there are some methods that want to support a query level. So uh, the methods I mentioned only support some workloads, given workloads, it supports workload tuning, and they tune some parameters, knobs that affect who did this. But some users only want to improve the query level. For example, we want to increase the performance of single query, and for example, a slow query. So how to optimize the query, a specific query or the specific type of query. So we need to capture the query encoding and the input encoding into the tuning. We can also support some session level. So, for example, we want to optimize the query in this session. So in this work, the author proposed different tuning granularities to achieve the performance for different scenarios. And there are also experiment paper for the tuning works. For example, they want to compare different methods, for example, Gaussian process, deep learning, and reinforcement learning. And they want to know the pros and cons of different methods. So there's some conclusions from the experiment paper. For the tuning performance, they are better than DN and better than Gauss processing. And Gauss processing can convert quickly, but may fall in some local optimal. And the DNN, and require some more training iterations, but find the better settings for adaptability. So DNN, and better than Gaussian process and tuning time. And the tuning time, if we want to run workloads, the running workloads take much portion of the time. So important to reduce the training time. So there are lots of work on tuning the buffer size. For example, the buffer is very important and to meet the user requirement, for example, SLA, service level agreement. So for example, the user wants to execute query within 1 second, how can we tune the buffer? If we can increase the buffer size, the query may be faster because most of data will be in memory. But if the performance is already meet the performance from the user, we can decrease the buffer size. How to evaluate whether the buffer size is enough to meet the SLE? I think this is also very important. And there's some learning by some method to work on this. And the next one is the buffer size tuning for Spark. So you know that Spark have many knobs, and the knobs in different levels, for example, resource management level and container level and application level. And in each level, there are some knobs, and these knobs have different effects for the performance. So how to capture the correlation from different levels. And next, how to select important metrics from each label, and how to combine the metrics and knobs from each level. So they work on this, and they use some direct based optimization to combine the different knobs from different levels. Here is a comparison of different methods. We compare a different method in different rows, and for each column is different metrics. For example, the tuning quality and the tuning latency and workload adaptivity and database adaptivity and hardware adaptivity. So we can say that the usually manual tuning usually have high tuning latency, and some heuristic can adapt to database, but it relies on some training data. And reinforcement learning can adapt to different database and hardware. And deep learning, because they rely on some training data, so it's not very easy to adapt to different scenarios. So some takeaways. So learning-based methods can find better norms than some search-based methods, and learning-based methods can take long training time because they need to run some workloads, and it's very important to study the adaptability to different database, different workloads. And there are also some open problem. For example, we want to predict workloads performance after the knob tuning. This is also important. We need to convince the user that after you tune the knobs, we can make the database run faster. How to evaluate this and how to guarantee this. And the next one, how can we use one tuning model to fit different database? So we have different database, PostgreSQL and MySQL. Can we have a single tuning model to support different case? And can we utilize some knowledge information? Because the human has some knowledge and human can inference and read it. But for computer, how can achieve this? Okay, next we will introduce some other components for database optimization.
Hello everyone, I'm Xuanhe Zhou from Xinhua, and my supervisor is Gu Liangli. Next, I introduce View Advisor. View modularization is rather important in DBMS that utilizes views to improve the query performance based on the space-for-time trade-off principle. However, it's hard to automatically generate and materialize views for ordinary users. Traditional methods rely on DBAs to generate and maintain materialized views. Unfortunately, even experts cannot handle large-scale databases. So let's first see the workflow of automatic view advisor. Given a set of queries, the view modularization just generates a collection of high-quality views to optimize for the future queries. It includes extracting the common subqueries and then estimating the performance and selecting from the subqueries as materialized views, and finally, rewriting the queries with materialized views. What's more, we also need to consider when and how to update and remove the useless materialized views in the future. We can divide existing MV works into MV selection and MV eviction. MV selection is an NP hard problem, and there are many problems in heuristics. First, traditional MV estimation is based on empirical equation, but it makes no sense when MVs change the query plan drastically, because it's hard to estimate the future refresh cost. Second, heuristic methods take MV selection as an LP problem and use greedy or heuristic rules to solve it. However, the performance can be very bad with assumptions like MVs with higher costs can have higher utility. Besides, traditional methods need to estimate the credit, that is the sum of future utility and the recreation costs, to decide whether to build the MVs. So, Oracle has proposed a hybrid MV selection method. The greatly select the MVs and predict trends with machine learning. The first generates candidate MVs that balance between conflict queries, and then it enumerates queries MVs and estimate the query costs with or without MVs. And finally, it selects the MVs with maximum cost reduction to actually implement. Besides, it also provides MV refresh, which predicts MV usage with a neural network. And if the usage has degraded to a threshold, they will drop the MVs. However, the downside of this method is that it still takes quite a long time to enumerate MV combinations and cannot ensure high performance with heuristic pruning. So to address these limitations, Yuan has proposed to use reinforcement learning to address view selection and maintenance problems. First, they use a wide deep model to estimate the benefit of using a materialized view to answer a query. Second, they model the view selection as an integer linear programming problem, or LP problem in short, to use reinforcement learning to find the best policy. However, they assume that the workloads do not change and cannot adapt quickly to different new workloads that have different query patterns. So to address this problem, Vue has proposed an encoder-decoder-based view advisor, which first extracts common subqueries across all the user queries and uses a deep encoder-reducer model to estimate all the queries together with the candidate MVs, and will take the embedding vector for the ARM architecture to select MVs. So the core idea here is the encoder-reducer model that can encode both the queries and the materialized views, where the encoder is an RN network that just embeds the query features, and then the reducer will encode the encoded query features together with the candidate materialized views into an embedding vector. Next, they utilize an attention mechanism to learn the relations between the query plan trees and the view plan trees, and will take both the attention vector and the hidden vector of the encoded reducer model as the state vector of the IR architecture. In IR, it takes the attention and the embedding vector as the state, and the agent decides whether to implement which MVs based on the state features, like common subqueries that do not have MVs. However, this method do not consider when and how to drop materialized views. It's challenging to decide whether the created MVs actually take effects for current workloads. So, how to drop the created MVs when there is no enough disk budget? For view eviction, a credit-based model is proposed that evicts materialized views with the lowest credit when the storage limit is reached. Higher credit means that we will sacrifice more utility if we evict the view. However, because they train the R model with the runtime of workloads, it assumes that the database environment will not change. This results in a high cost of model training, especially in the code startup step. In this table, we have summarized the advantages and the disadvantages of different selection methods. And we can see that the encoder-decoder model has achieved the highest quality because it encodes the query features together with the materialized view features. And based on that, the IR agent can decide which materialized views can achieve the highest utility, while other methods only based on some heuristic rules, the subqueries only. Besides, the MV eviction methods have achieved the highest adaptability because it can dynamically decide which materialized views are actually useful based on the incoming queries. So in conclusion, learned MV utility estimation is more accurate than traditional empirical equations. And learned MV utility estimation is more accurate, especially for the problems like multiple MV optimization. And learned MV selection is more robust than heuristic methods. And learned MV selection works well in online service that takes much time for model training, especially for code start steps. And the query encoding models need to be trained periodically, especially when the data are updated. And there are some open problems like MV benefit prediction for the incoming queries, and the cost of MV initialization and the future updates, especially for the learning-based methods. And besides, we need to decide how to support both MV updates and MV evictions together. Next, we are going to introduce the index advisor. In DBMS, indexes are the key to speed up query execution, and one of the most important problems is index selection. First, to build an index for a specific query can get a very high cost reduction. However, index selection is an hard problem. It needs to select from numerous candidate indexes. Besides, it's not the case that we build more indexes and we can gain higher performance. If you build some redundant indexes, they may consume too much memory space, increase the maintenance costs, or even cause negative effects. So first, let's also see the workflow of the learn index selection. Given a set of queries, you need to generate a collection of indexes to optimize the execution of queries. So it mainly includes four modules, including the circle feature extraction, index benefit estimation, index cost estimation, and the index selection. And we can see there are many challenges in index selection of each module. First, it's hard to estimate a benefit since there are multiple features like execution time and the space budget. Besides, there are interactions between different indexes like a multiple column exercise where you can build an index or multiple columns. Besides, the set of possible index combinations are huge and they exponentially increase with the number of columns per index. We have divided in existing index selection methods into offline index selection and online selection. First is offline index selection. The basic method is auto-admin. For each query, it extracts the indexable columns and enumerates for the column combination with the highest index benefit. For all the queries in the workload, it runs top K combinations and greatly adds indexes until arriving the limited disk space. Another similar method models the index selection as a knapsack problem and uses dynamic programming to select the highest benefit index combinations. And another class is online index selection, which is also horizontally. Consider a what-if-based method that divides the workload into epochs of queries. And for each epoch, the profile the candidate indexes for the incoming new query. For the incoming query, it estimates different benefits of the indexes that can be used by the query, and will update the index set based on the newly found indexes. And finally, at the end of each epoch, it will create the indexes with the highest index benefit in the set. However, the what-if-based method, it is laborious to require human beings to design the what-if calls. So another idea is we just use the DBAs to estimate whether the selected indexes are good or not, and other things are left for the automatic algorithm. So there is a semi-automatic index selection method. It monitors the DBMS in real time and then dynamically analyzes the workloads and enumerates some candidate schemes and to tune enumerate some candidate schemes to tune the index structures. But before implementing the index schemes, it calls the DBAs to judge whether the scheme is good or not. And based on the feedback, the well updates its selection strategy. At some level, this method has reduced the DBA's burden. And recently, machine learning-based index selection methods just consider whether we can replace the feedback part with machine learning models. So the core idea is that it thinks that it's critical to compare the execution costs of plans and decide the index benefits. In simplicity, we only consider whether we can gain the performance improvement after creating the indexes. If yes, we just build it. If not, we just ignore it. So this method builds an evaluation model to create indexes with performance gains. This table has summarized the differences of both selection methods. And we can conclude that the learned methods mainly outperform traditional methods in index benefits estimation, and the learned index selection can efficiently work in query level, but ignores in the interactions between the queries in the workload. And the traditional index selection, they cannot adaptively balance between the index benefit and the maintenance costs, for which the learning-based methods can do a better job. Besides, there are also some open problems in index selection. like how to build an online learning-based index advisor that can support online index selection and index updates. Besides, how to improve the adaptability for different database schemas and memory capacities. Next, we will introduce the database partition on distributed databases. Most of the existing methods are horizontal partition in table level. It's extremely important to place different partitions across the nodes to speed up the query execution and balance data distribution. However, database partition is NP hard and needs to enumerate many different columns, and the candidate combinations can be very huge. And finally, the existing partition functions like hash or round robin are too simple to process complex transactions, and the range function requires careful manual design. So database partition is to select columns as a partition key for each table and use the partition keys and the partition functions to locate the rows of those tables into different partitions to achieve higher execution performance. So in the following, we'll separately introduce existing works in partition key selection and partition key design. For partition key selection, the first method is search-based, which is mainly composed of two steps. For the first step is to maximize the data locality. That builds a table-level graph where the vertices are tables and the edges are joint predicates of each query. And then it derives a maximum spanning tree on the graph whose edges can be used to co-partition the tables. However, co-partition can cause data redundancy. So in the second step, for each query, it can derive a spanning tree, and to minimum the data redundancy, they recursively merge those trees by dynamic programming. However, this method still brings in much data redundancy in the end. So there is also a deeper reinforcement learning-based method. They first encode the tables, query frequencies, and the foreign key constraints into a state vector and use the deep reinforcement learning model to select a partition key or a replication table at each iteration. They can learn from the reward to optimize the selection policy. It computes the reward based on the causes estimated by the optimizer, which is not available before partition. So in other work, they design a simple custom model based on the neural network. However, this neural network can only work for single queries, and they just ignore the important partition factors like data allocation or concurrent queries. So another problem is how to design the partition functions to support complex scenarios. The first work is for small transactions, which may access multiple nodes and bring extra overhead than on the single node. The method includes three main steps. First, they also build a graph model, right? And the vertices are tuples, and the edges are the transaction relations. For example, for the tuples in the same transaction, they all have edges between each other. And then they use the graph partition algorithm. First, they build a graph model, right? The vertices are tuples, and the edges are the transaction relations. For example, the tuples use the same transaction, all have edges between each other. And then they use a graph partition algorithm like a matrix to locate the nodes into the K partitions. However, until this step, we still do not know how to partition the tables because it uses the range partition function to locate the tuples. Hence, with the tuples as the values and the K partitions as labels, they build a decision tree and derive the partition ranges based on the tree of predicates or values leading to the leaf nodes. However, as declared in this paper, it's not ideal for very large databases or workloads with heavy inserts. Another partition function is for analytical queries that reduce the latency. That also mainly has three steps. First, it identifies the query filters as features, and then we can characterize each tuple with a bit vector, and each bit represents whether the tuple is used in the query filter. And finally, they just found the optimal partition from bottom up with a clustering-based algorithm. In this table, we have summarized the differences of the partition methods. And we can see the learning-based method, like a DRL for the partition selection, they can achieve the highest quality by considering more partition-related features and use the agent, the R-based agent, to explore and exploit the selection policy. However, it still has very poor adaptability for different workloads and data schemes. So in summarization, the learning-based selection methods, they can outperform the heuristic partition methods, but has much higher partition overhead for model training. And the graph partition-based functions, they can outperform traditional functions like a simple range or Hashi partition, but they still cannot work for some complex scenarios, like partition for join queries or large-scale data sets. So there are still many open problems, like adaptive partition for relational databases, the partition quality prediction, which is especially important for learning-based partition selection methods, and how to improve the partition availability with replicates for like on the small tables. Okay, let's enter the next section, the database optimizer. The first problem is the cardinality and the cost estimation, which is commonly seen as the heart of database optimizer. However, traditional methods are very simple. For cardinality estimation, is to estimate the size of the SQL query's results. They are based on the sampling or kernel-based methods and cannot accurately estimate the results. And for the cost model, histogram-based methods, meaning model the data distribution of single columns and fail to work for multiple columns. And sampling-based model methods also have the performance degradation problem. For supervised query methods, they learn a mapping function between a query and its cardinality on the same databases. They treat the cardinality estimation as a typical regression problem in machine learning. They first train the query models with the sampled queries and their corresponding cardinalities, and then use the trained models to estimate the cardinalities of online SQL queries. To learn the cardinality of join queries, traditional join sampling fails to work when there are no suitable indexes or mid-severe sampling degradation. So one work just proposed a deep learning-based method that uses the linear models to encode different parts of circles, like the table, joins, or predicate features. And then they concatenate the different parts into an embedding vector. And finally, learn the network parameters to fit the mapping from the query features to the actual cardinalities. And another challenge is that there may be correlations between the multiple columns in the same table. Traditional methods, they just require to assume column independency, which may not work for this scenario. So learning-based method, they use a chain-based assembling algorithm to solve this problem. They first use the local neural network to encode different predicates on a fixed join path of the query. And since a query plan is a binary tree, they use tree-based assembles like a charge boost to pass the encoding vectors of the query through the traversal of multiple binary trees and outperforms the average value as the estimated cardinality. Instead of assuming independence between the columns, these network parameters are used to fit the mapping of queries to cardinalities. Another class is supervised data model that learn the data distribution model based on some SQL queries and their real cardinalities. During supervised learning, they sample some data based on the query predicates and train the data distribution model to output the probability of the query ranges. And then in cardinality estimation, they uniformly sample tuples and use the data model to compute the cumulative densities of all the selected samples, whose sum up is taken as the estimated cardinality. So the first challenge is how to select a powerful distribution model that can work for so many rows in the same table. One work is to use a kernel density-based estimator for this problem. They first sample some rows from table and initializes the bandwidth of the kernel density estimator. And then it picks the optimal bandwidth via the stochastic gradient descent. Besides, Park also proposed a query-based method with maximum models. The maximum model is the probability density functions for fitting the observed predicates and the selectivities of predicates by minimizing the differences between the models and the observed distribution. They adopt two ways to represent the X data distribution. The first is sampling-based. The generates multiple random points, creates subpopulations and points, and estimate the excess selectivity based on the maximum model learned from the subpopulations. And the second is cluster-based. On the sample data, it clusters the points based on the smallest rectangles that covers all the points, which may have more subpopulations to learn but has higher accuracy. This method can efficiently avoid the overhead of multi-dimensional histograms. However, it still cannot support some complex queries with lack or excessive keywords. And the last class is the unsupervised data models that can directly use the data to train the data density models. They first sample some reasonable amount of, the last class is the unsupervised data models that can directly use the data to train the density model. They first sample reasonable amount of tuples uniformly, and then they input the data tuples into the data model to learn the joint distributions. And finally, they sum up the cumulative densities of all the selected samples as the estimated cardinality, like the second class, right? However, to learn the joint probability distribution over all the columns, and efficiently support the cardinality estimation for range queries, Yang has proposed to use the autoregressive density model to represent the joint data distribution among columns. The model returns a list of conditional densities present in the chain rule with an input tuple. To support the range partitions, the model adopts progressive sampling to select the meaningful samples by leveraging the learned density models. It works even with scored data. However, it cannot support high-dimensional data or multiple table joins. So, as we see, the deeper AI models can only handle single tables, and then we need to learn from join correlations. This method has solved the problem that it can be both the deeper AI model and the joint sampling method. First, it learns a single autoregressive model for all the tables. And second, the joint sampler provides correct training data, like sample tables from join, by using the unbiased join counts. Lastly, it downsamples some tuples from the large table when estimating the query, with only a subset of tables, according to the fan-out scaling. However, to learn the joins of all the tables, it can be very time-consuming, especially when the dataset is a bit large. So it is still challenging to estimate for the join queries with a poorly data-driven method. There are also some product network-based method. It mainly aim to solve the problem that some data in the tables may have different distributions and they are independent from each other. So in this method, they first split the data table into multiple segments based on independency relations, and the columns in each segment are nearly independent. And then they build a relational sum and product network, where the sum is for the future operations, and the product is for the joint operations. And to support the aggregates like average and the sum, they multiply the expectations of the aggregates with the probabilities coming from the child nodes. Another important problem is the cost estimation. So what's the different from the canality estimation? First, cost estimation is to approximate the execution time of resource consumption, where canality only talks about the resultable size. And the cost estimation is also based on canality in the traditional database optimizers. And the cost is much harder to estimate than canality estimation because then it needs to consider multiple factors like sequence scan costs in the physical level. So there are relatively rural works in cost estimation. One work is to solve the problems in traditional cost estimation that can only use the estimated canality to further consider the cost, which is inaccurate without the encoding of query predicate. So Sun has proposed an encoding learning-based cost estimator with a tree-structured STM that learns a representation for each subplan with physical operators and predicates and outputs the estimated canality and the cost simultaneously by using another estimation layer. Moreover, the method encodes keywords in the predicates by using the word embedding. So in conclusion, for canality estimation, the data models are more effective for single tables. Query models are more effective for multiple tables because the sampling time for the data models are too time consuming. And query models are more efficient than data models, especially for the learning of data distribution model. And data models are more robust than query models because it only learns the underlying distribution and work for different data or queries. And training queries are vital to the query models, and samples are crucial for the query models. And for the cost estimation problems, the estimators based on neural network are more accurate than the statistic-based estimators. And the statistic-based query model is the most efficient. Next, I see the plan enumerator. Traditional optimizer just relies on heuristics or dynamic programming to select high-quality query plans like operator selection and join order selection. However, the plan space is very large. A traditional optimizer cannot give a very high-performance plan within limited time. So there are two kinds of learning-based join order selection methods. The first one is offline. It uses existing workload to train a learn optimizer, and the learn optimizer will predict the plan for future workload. And another is online methods, in which the plan of a query can be changed during execution, and the query can switch to another plan if it finds a better plan, and it can learn when the database executes the plan. Two recent works have been proposed to use deep reinforcement learning to reduce the search space for offline learning. Similar to dynamic programming, we first model this process as a Markov decision process, and the optimizer is an agent, a join is an action, and the environment is the cost model or database. The reward is our cost or the true latency, and the state is our join order. The picture on the right describes the numerical decision process of the join procedure. In the beginning, we have the initial state of 4 independent tables. Each time we select the 2 tables to join, we got the intermediate state. After 3 join actions, we get the final plan, and this is the termination state. Moreover, the ball tool methods cannot support updates on schemas. To address this problem, RTOS uses a two-stage training to generate better join order on latency with a well-designed neural network structure. In order to address the problem of caching the structure of a join tree, RTOS proposes a model that utilizes the tree LSTM to represent the join state. The RTOS first designs the representation from column, table, and join tree. Then the DQN is used to get the join order generation after the representation is obtained. Next, RTOS first uses the cost to pre-train the DNN network, and then utilizes the latency information to fine-tune the neural network online. And the experimental results and find that it can have a very high performance for different database schemas. Another class is the online learning-based methods. This class of methods focus on learning a join order using adaptive query processing, which can change the join order even during the execution. Anu has proposed an adaptive query processing mechanism called adding, which combines the execution and the optimization of a query. It learns and generates the join order during the online execution of a query. First, displays the query process as many operators, like 2 join operators between 3 relations in this picture. And adding uses 2 routing methods to control the order of this operator, like the naive, just greedy-based, and the lottery, the probability-based, to handle the incoming tuples. Besides, Chalmers proposed a Monte Carlo tree search-based method called SkinnerDB. SkinnerDB uses the MCTS instead of other reinforcement learning-based methods like Q-learning because it provides theoretical guarantees on cumulative regret over all the choices. And SkinnerDB divides the query execution into many small time slices, and in each slice, the chooses 1 join order to execute, using the real performance of a join order in the time slave. SkinnerDB trains the Monte Carlo tree search to get a better join order selection. And finally, SkinnerDB merges the tuples produced in each time slice to generate the final results. This table has summarizes different methods for join order selection and plan enumeration. And we can find that the learning-based algorithm usually gives the plan with low time complexity, especially for large queries. And the offline learning methods use the sample workload to pre-train the model. It will give very good plans for the incoming queries on the same data size. And a new database will lead to model retraining for both the offline and online methods. Online learning methods does not need previous prepared workloads and can give very good plans even for dynamic query processing. But it needs the customized engine, and it's hard to be applied in existing databases. So that's a key problem for online learning-based method. And there are many realistic open problems, like how to raise the generalization performance of offline learning methods for the unseen queries, and how to ensure the plan given by the learned model is robust, and how to speed up the model training time, like transferring the previous knowledges, and finally, how to make the model aware of the data updates. So let's first see the basic idea of learn index. Tim has proposed that all the indexes are actually models, where the B tree index can be seen as a model that maps each required key to its page. For a sorted array, larger position ID means a larger key value, right? And the range index should effectively approximate the cumulative distribution function, or CDF in short. Based on this observation, Crosscap has proposed a recursive model index, which uses a learning model to estimate the page ID of a key, and this method outperforms B plus tree and the in-memory environment for relatively small data size. However, they cannot support data updates, and it doesn't show the effectiveness for secondary indexes. So there are still many challenges for practical learning-based indexes. First is how to build a multi-dimensional indexes. We know that to utilize a multiple dimension index, we need to decide which columns are accessed together and carefully arrange their access orders. And the second challenge is how to support updatable indexes, like inserts, deletes, or updates that will severely modify the data distribution, which require learning-based index models to support dynamic data modifications. In this taxonomy, we can see that the current learning-based methods can be divided into immutable learning indexes and mutable learning indexes. For the immutable learning indexes, there are one-dimensional index like MI, which is a hierarchy architecture where each model picks another model based on the input keys until the final stage and predicts the position. And there are also multi-dimensional indexes like a float, which models each attribute using the recursive model index, just as the RMI in the cell divided by the optimal layout. And for the mutable learning indexes, there are fixed data layout index like LEX, which dynamically adjusts the shape and the height of the RMI index depending on the workload to provide more robust performance even when the data distribution is good or dynamically changed. And for the time limit, you can find more details in the related tutorial in SIG Spatial 2020. And we just do not give more details here. And another problem is how to design more complex data structures, since traditional data structures like the secondary indexes, hash map, blue filters, they are also unaware of workload or data characters. So instead, we can reconstruct the data structures for higher performance. In the learned key-value storage design, Addressor has shown that data structures in key-value storages can be constructed from fundamental components, and the learned cost model can guide the construction directions. They define the design space as all the designs that can be described by fundamental design components, such as fence pointers, links, and temporal partitioning. And design continuums is a subspace of design space, which connects more than one designs. To design a data structure, the phase first identifies the bottleneck of the total cost, for which the model can be tuned to leverage it, and then tune the knobs in one direction until they reach its boundary, or the total cost reaches the minimum. This process is similar to the gradient design in machine learning, and can be conducted automatically. So in conclusion, the learning-based method opens up a novel idea to replace traditional data structures like an index and show good performance in small data sets. And the learning index uses machine learning techniques that can provide the probability to combine the new hardware. And though some research has already verified the benefit of learning indexes, the performance in industrial level scale still need to be studied, especially in updatable and multi-dimensional situation. And there are still several open problems, like how to support learning index in distributed system, and how to support more large data scores, and improve the stability of learning indexes. Next, we introduce transaction management. The motivation includes that you need effective transaction scheduling, and that can significantly improve the performance by minimizing the resource or data conflicts between different transactions. And it's challenging to control the concurrent queries or transactions. And besides for the transaction management, there are different cases like transaction prediction or transaction scheduling. First, for the transaction prediction, it's important to database optimization like resource control or the following scheduling tasks. While traditional workload prediction methods are rule-based, they just identify the signals like internal latency or resource utilization in the database that are relevant to the workload characters, and builds a statistical model for the workload prediction, which can consume much time. So Ma has proposed a learning-based method to predict the future trend of different workloads. In the first part, it identifies the query templates and the arrival rate from the workload, and then it combines templates with a clustering-based algorithm based on the arrival rate patterns, and finally, the will forecast the arriving rate of the new queries based on the clustering method. Another work is transaction scheduling. Traditional database systems add schedule workloads sequentially, which cannot consider potential conflicts or schedule the workloads based on the execution causes predicted by the database optimizer, which may be very inaccurate. So Zhang has proposed to learn to schedule queries to minimize the disk access requests. It first collects some the state of the request data blocks from the buffer pool, and then it will featureize the state features like buffer pool size and the data block requests. And finally, it just schedule the queries to optimize the global performance based on the state features with the IR method like Q-learning. After that, we will introduce and we can see that current transaction, and we can find that we can use the deep learning for the transaction management. We mainly has two observations. First, for the transaction prediction, simple neural network cannot efficiently support concurrent query features that have complex correlations. So they just propose some more complex models like clustering-based or the graph embedding-based. And for the transaction scheduling, they still use the classical reinforcement learning-based method to optimize the policies. So we have two observations for the transaction management. For the transaction prediction, we can see that simple neural networks cannot efficiently learn the correlations or the patterns. So there are other methods like RNN or more complex the graph embedding method. And for transaction scheduling, they still adopt the classical reinforcement learning model to optimize the policy, but it is still time consuming for the exploration process. Next, we will introduce the self-monitoring and the diagnosis part. For an autonomous database, generally, they collect performance-related metrics like resource utilization or L metrics, and detect abnormal metrics and the diagnosis corresponding root causes. This is the whole circle of the self-monitoring and the diagnosis procedure. So the first problem is how to proactively detect the database performance. There are works that predict performance changes, especially for the concurrent queries. The traditional prediction method only captures the logical L metrics and neglect many result-related features and cannot get very accurate results. So Marcus has first proposed a deep learning-based model to predict the query latency and the concurrent scenarios, including the interactions between the child parent operators and the parallel plans. However, they just denote the child operators and the parallel plans as the tree nodes and cannot capture the operator-to-operator relations like data sharing and conflict features. So Joe has proposed a performance prediction method with graph embedding. They use a graph model to characterize concurrent queries, where the vertices are operators, the edges capture the operator correlations like data parsing and axis conflicts. And they use a graph convolutional network to embed workload graph, extract performance-related features from the graph, and predict performance based on the features. After detecting the abnormal performance of metrics, next we need to diagnose the root causes. There are three motivations. First is that the system performance problem is very common, especially on the cloud databases. And traditional diagnosis highly relies on DBAs and the experts, and is very costly and time-consuming. The AI methods can utilize historical data and rules to enhance the diagnosis procedure. Based on the workload types, we can divide existing diagnosis workloads into RTP-oriented and OLAP-oriented. First, for the system diagnosis for RTP, the meaning takes the whole workload into consideration. One method designs a machine learning algorithm to extract abnormal metrics and utilizes a causal model to diagnose the potential causes. They collect the statistics and merge statistics based on the time step, and then explain the root causes with the causal model, where each root causes is a cause variable with several effect predicts like the CPU weight, latency, and the disk write. Another approach is also based on DBA's experience. They assume that some slow queries with similar key performance indicators have the same root causes. They adopt a two-stage diagnosis. In the offline stage, they extract slow queries from the failure records, cluster them based on the KPI state, and ask DBAs to assign the root causes to each cluster. And in online state, for an incoming slow query, they match it to a cluster based on the similarity score of the KPI state. If matched, they use the root cause of the cluster to notify DBAs. Otherwise, they generate a new cluster and ask the DBAs to assign the root causes. However, this method cannot prevent potential database failure. So another method is system diagnosis for OLAP. Queries in analytic workloads are parallelly executed, which can be modeled as a DAG of stages. So is to compute the resource contention between the queries and the causes of execution slowdown. In this method, they first build a graph in multiple levels, like a query level, resource level, and a server level, and detect the victim queries and explain the causes of the victim queries by traversing a path in the DAG from some nodes in the level 6 to the victim query. Another interesting solution is to unify the diagnosis on database like a PostgreSQL and the SAN storage. The core idea is to build a noted plan graph from the workflow of the query execution. They first builds a graph by parsing the query plans as a tree, and then it will correlate the operators in the sum model with the nodes in the tree. And then it will compare the newly built tree with the historical data and judge whether the query plan has changed and which operators consume much more time. And finally, the will analyzes the operator correlations and judge the important operator size. And finally, the will diagnoses the root causes based on the important operator size by matching with previous problems that cached in the knowledge base. Yes. So in this table, we can summarize the differences of the different system diagnosis methods. And there are some more general for both the RTP and lab workloads diagnosis methods in the commercial databases like Oracle. However, all of those methods, they are knowledge-based, and the most current methods are not very efficient in using the DBS expert and the machine learning techniques. So in summarization, load monitoring works better and can largely reduce the problem detection latency and save the manpower. And the current learning-based monitoring method still needs DBS to decide the key metrics, and they cannot automatically decide which metrics are important in different scenarios. And learned performance prediction provides more accurate execution information than cost estimated by the database optimizer because they can consider more execution-related features and the correlations between the physical operators. And since different databases may have different execution mechanism, it's extremely difficult to migrate the learned monitoring methods to different databases. And most existing technology works rely on expert experiences, and we need to some further knowledge and insights to combine the expert experiences and the machine learning techniques. So there are actually many open problems like diagnosis on low cost and they to obtain statistical metrics. And we need to diagnose for parallel transactions like D-trace. And finally is the data security. We can find that there are different aspects that are very important in database security. The first is sensitive data discovery. Since the leakage of sensitive data can cause great financial and personal information loss, it's important to protect the sensitive data in a database. However, traditional methods use user-defined rules. With learning models, we can automatically learn the real access frequency of data records. And the second issue is access control. It aims to prevent unauthorized users to access the data, including the table level and the record level access control. However, traditional methods are based on static rules. With learning models, we can customize policies to regulate the data requests based on both actions and the data access patterns. And the final issue is the SQL injection, which is very common and harmful to databases. Attackers may modify or view data that exceeds their priorities by passing additional information. Traditional methods take a very long time in scanning SQL injection. With a learning model, we can classify different SQL injection actions and use techniques like fuzzy networks to automatically learn the attack patterns and prevent SQL injection. Finally, we will introduce some more autonomous systems that integrates the above learning-based techniques in databases. There are several motivations for the autonomous database systems. First, traditional database design is laborious. We may need to develop both the system and the data structures based on the X patterns. Otherwise, the general modules may not work well in all the cases. And most AI4DB works only focus on single modules, which can cause local optimum. Besides, there are some commercial practices of AI4DB works And we can find that the heavy machine learning models are hard to implement inside the database kernels, and a unified training platform is required. So the first vision is Part1 that Paolo just proposed to predict the workload arrival rate with clashing RN and deploy the optimization actions based prediction results, and they can optimize databases with actions like knob tuning or index or machine learning materialized view selections. And the SecDB has also proposed a vision to specialize the database implementation by learning the data distribution, like learn the CDF models and designing the database components based on the expert knowledge and the CDF models, like the learn index or the query scheduling and other physical operator optimizations. Since about 2 did not implement in the real scenarios, Lee has proposed the OpenGauss, an autonomous database system that validates, trains, and implements state-of-the-art learning-based components in an open source commercial database. They build an autonomous database framework and integrates their proposed learning-based database techniques into the open source database system, like the learning-based query writer, the cost estimator, and the plan enumerator. And for the outside maintenance, they also support the self-monitoring, self-diagnosis, configuration, and optimization. Besides, they also devise an effective validation model to validate the effectiveness of learning models. So in conclusion, AI can solve many tricky issues in databases, like high-dimensional regression and NP-hard problems. And AI can help to automate database optimization and maintenance, especially on the cloud. And besides, current AI4DB was mainly focused on overlap workloads, where data is rarely updated and users are not sensitive to the training latency. However, for OLTP, the data may be frequently updated, and users may require very high model inference efficiency and robustness, which are great challenges for current AI techniques and requires more system and algorithm designs.